So I've also added, which is only right, my collaborators in a lot of the stuff that I'm going to show. Ned Patton from NCAR, who's responsible for all of the videos you'll see, and Roger Shaw, not Roger Shaw III. I forgot to click the thing which makes it a superscript, but Roger's from UC Davis, at least. I think they still pay him a pension, although he lives in Nova Scotia now. So just where we went out of the cinema the last time on Wednesday, we tried to emphasize these points, that canopy and rough to sublayer turbulence is more efficient at transport than turbulence in the inertial sublayer, the surface layer above. There's a single canopy length scale that's much larger than wakes of leaves, and it works in modifying Monod-Novikov similarity theory. So we're talking about dimensions and parameters. We have to add another parameter now to modify Monod-Novikov as we get close to a deep rough surface like a canopy. And this is not the distance between individual trees or anything like that. It's the average absorption length of momentum in the canopy. You can actually do a one-dimensional calculation and show that if you could suddenly accelerate wind into a tube full of trees, it would take this length before it was 1 on E towards equilibrium. The origin of these large canopy eddies has been a sort of a guiding question in canopy turbulence for, at least 30 odd years. And, certainly I studied my PhD working on this, and many other people have contributed, including this guy at the front here. So in this talk, what we'll do is explore the origins of these canopy eddies in a little more detail, and then step back a bit and look at how these couple to the motions in the whole boundary layer above, the stuff that Matthias was talking about this morning. So again, I've given a sort of contents page for people who are looking at this talk afterwards. So let's start going back a few steps. That's the flux tower at Tumbarumba. It's a 60-meter tower. Actually, I think it's 55-meter tower because the last 5-meter section fell off the back of the truck as we were going through the forest and bent, so we weren't allowed to put it up. But it's actually in the roughness sublayer because those are 45-meter high Eucalyptus delicatensis, alpine ash trees. It's a regrowing forest which is about 40 or 50 years old. So from a single, there are many other sensors on that tower, but from a single sensor like that, you can measure the probability distribution functions, joint probabilities of vertical and horizontal wind speed fluctuations. And if you do that and just follow the trace through time of U prime, the horizontal fluctuation and vertical fluctuation changes, you get what's essentially a probability distribution, a probability density function. So up in the surface layer, well above the canopy, we see that the probability density function is kind of an ellipse tilted on its side, so that there's more probability that when the wind speed is going is higher than average, and the vertical velocity is down, so carrying high speed fluctuations towards the ground, or when the wind speed is lower than average, the vertical velocity will be up, therefore carrying negative momentum away from the surface. Those two quadrants, so-called, the Q2 and the Q4 quadrant, the trajectory stays in those quadrants more often than it stays in the Q1 and Q3 quadrants, which would be faster moving up or slower moving down. And we call that Q4 quadrant the sweep quadrant because it's fast moving air going towards the surface, whereas Q2 is the ejection quadrant, it's slow moving air coming away from the surface. And it has that sort of balance thing where there's perhaps a bit more time that the trajectory stays in the ejection quadrant than in the sweep quadrant. But it certainly spends more time in those two quadrants than in the other ones, which are actually called inward and outward interactions. Now, when we get down into the canopy, or just above the canopy in the roughness sublayer, we can see that the sweep quadrant is much more important. So the probability of finding times when the wind speed is stronger than average and down towards the ground is higher than the other, certainly higher than the ejection quadrants and much higher than the inward and outward interaction quadrants. So we have this picture that sweeps dominate momentum transport near and just in the top of the canopy. And in fact, if we plot the ratio of sweeps to ejections or ejections to sweeps, Q2 over Q4, through the canopy airspace and up into the roughness sublayer from a variety of different canopies, we see that that peaks. So in the upper canopy, the sweep quadrant is probably twice as big as the ejection quadrant. So much of the activity in the upper canopy is dominated by sweeps. I showed you some pictures from this tower, the Camp Borden Tower in Canada, a facility run by Roger Shaw for years, and this was these familiar plots that you've already seen were collected during the Boreas experiment, where many towers were measuring at the same time. So we saw these scalar ramps where the temperature increases with time and then drops suddenly. And we have seen these at different levels through the canopy at about 6 meters, 10 meters, 15 meters, 20 meters. Is that? Yeah, 20 meters. It's around the canopy top and then above the canopy. And we can see that these sudden drops in temperature are correlated right through the canopy airspace. So when the sweep quadrant comes down, it's bringing cooler air from above and replacing the warmer air that's moved out of the canopy in front of the sweep in the ejection quadrant. So the coherence of these structures was, was one of a whole series of pieces of evidence that were building an edifice that was telling us that large eddies dominate canopy transport. So again, by focusing on that large drop in temperature, the scalar microfront, Roger and co. Composited the velocity vectors and the temperature contours and gave us this picture where the ejection quadrant, where the slow-moving air is moving up, leads to slow-moving warm air is moving up, then suddenly changes through the sudden drop at the end of the ramp into cooler air moving down through this so-called scalar microfront, and the cooler air moving down is associated with this fast sweep. So this idea of the ejection microfront sweep is sort of fairly solid through lots and lots of measurement campaigns and data. Someone asked me about this a couple of days ago. There's a series of papers by Yves Brunet with Serge Collineau, I think, which looked at a lot of data and fitted wavelets to them. And this sort of ejection microfront sweep is, as I say, one of the characteristic features of canopy turbulence. So, as I said, getting three-dimensional structures for these things, deducing what the structures are, is difficult from measurements on a single tower, even when you have many levels and long time periods. So we go to different tools like the large eddy simulation. This is Ned Patton's earlier large eddy simulation model with a canopy. So this goes up to actually 10 times the canopy height. We're only just showing the lowest 6 canopy heights here. And you can see in the scalar picture, the bottom one, those scalar microfronts, those sharp areas where the scalar contours, the temperature contours, are pressed close together. And again, just reminding you what we found the last time was that if we're on a surface which basically we're not interested in the details of the roughness, we can assume that or we can regard it as if the momentum is being absorbed on the plane. Then we get a boundary layer surface, basically a surface where the gradient of velocity decreases steadily linearly with height, which produces a logarithmic profile of the velocity. If we have a deep roughness layer where the momentum is absorbed not at the surface but over a height range, then we have to define a virtual origin at the displacement height, and then we modify our coordinates, so we still have a log law, but now the coordinate is z minus the displacement height. And the displacement height marks the centroid of the drag force on the canopy in the height. If all the momentum's absorbed before it hits the soil, then that's all right. If some of it gets through to the soil on the sparser canopy, then you've got to include the soil drag as well, or the drag on the actual surface. Now, we also talked very much about the fact that the velocity profile within the canopy is exponential or concave, whereas the velocity profile above the canopy is logarithmic or convex. And through fairly simple scaling arguments in this area above the canopy, because there are no sources and sinks for momentum and for horizontal momentum, and because we're assuming there's no accelerations in the flow, we only have a limited number of scales that things can depend upon, then it's inevitable that the gradient of velocity has to keep increasing down towards the surface, because the eddies doing the transport are getting smaller and smaller, and if you like, they're connecting two layers of different speed, and if the connection is smaller, then the difference between the two layers has got to be higher in order to keep the flux of momentum constant. Down in the canopy, it's a bit different, because now what we're doing is absorbing momentum as drag, but we're absorbing it as drag proportional to u squared, so you absorb it very fast to begin with, and then as you go farther down into the canopy, there's less momentum, so you steadily absorb it less. So the quadratic nature of the drag force gives us this particular exponential profile, plus the fact that the eddies doing the transport, we're assuming, are of constant size now. So with momentum being absorbed across a height range, it could be trees, it could be grass, it could be stones, really, if you're interested in that level. It could be buildings, so urban canopies in many ways behave like plant canopies at this broad level. Then you always get an inflection point between the boundary layer profile and the canopy profile. Now, I said in that first talk that if you have a boundary layer profile, then you won't get this thing going unstable and generating turbulence unless you add some viscosity to add a kind of a phase delay between fluctuations in inertia and pressure. But if you have an inflection point in the profile, then think disturbances will grow even if there's no viscosity, as long as the inflection point satisfies certain conditions. So Lord Rayleigh in the 1800s said that the necessary condition for disturbances to grow is that there be an inflection point, that the second derivative of velocity with height will go through zero. But Fjortov added a sufficient condition to this that said that not only do you have to have an inflection point, so obviously that's stable because there's no inflection point, and so is that. Here's an inflection point, but it's in the wrong sense. So Fjortov showed that that will still be stable, but an inflection point like this is unstable. I won't go through the arguments for it, but you can easily demonstrate this by noting that an inflection point like that means that there's a peak in vorticity at the center line and it decays on either side. So you can do a simple argument looking at displacement of parcels of vorticity and show that in that case, they will both be amplified if you move them off the center line. So what you get then, if you like, is a growing wave of vorticity. It's called a Kelvin-Helmholtz instability, which is a more general instability, which often includes a density difference, but even without a density difference, you'll get a particular kind of growing instability. And the wavelength of the instability is linked to the length scale of that inflection point through a scale called the vorticity thickness. Now, 20 odd years ago, 25 years ago, Mike Raupak and Yves Brunet and I were working on trying to understand the origin of these large eddies. And the things that we talked about, the fact that turbulence near the canopy top is more energetic, more coherent than turbulence in the boundary layer above, started looking for, what could it be that's going on? And then we knew about inflection point instabilities, and realized that mixing layers, which are studied often in engineering fluid mechanics, mixing layers occur when you have two streams of fluid of different speeds on either side of a plate, and then when they mix, when the plate ends as it starts to mix, you automatically get this inflection point. And in the mixing layer, you get very coherent eddies, where it's often done by marking the air on one side differently to the other. One might be hot and one might be cold, or maybe different gases or whatever. And then you can visualize it with a shadow graph or a Schlieren. I think this is a shadow graph. And you see these large eddies start to sort of gulp from above and mix it with air being dragged up from below. So there's a coherent mixing for a while. And this large eddy mixing is much more efficient than what's going on in the fully developed turbulence of the boundary layer here. Another way of thinking of this is that the eddies which are produced are very young down here. They haven't had a long straining history, whereas the eddies in the boundary layer have had a much longer straining time. So the strain you can calculate by integrating the shear, du by dz, over time. And you find that the average strain of eddies in the inertial sublayer, the log layer, are about 13, whereas down in a mixing layer, a young mixing layer, they're more like 1 or 2. And when we look at the statistics of turbulence in the mixing layer and in the boundary layer and compare them to what we see at the top of the canopy, it becomes immediately obvious that the turbulent flow near the top of the canopy looks more like a mixing layer than like a boundary layer. And again, we've had chats with a few people and asking about what really turns you on in science. This was one of these moments. We were beavering away at this stuff, and Mike went away one weekend and came back with this graph. And what he'd done was to take the whole series of measurements of the large eddies done by spectra or two-point correlations, all sorts of different methods, in a wide range of canopies, ranging from 5-centimeter wind tunnel models to 30-meter pine forests. And he plotted the spacing between the large eddies against a measure of the vorticity thickness. So the vorticity thickness in an inflective profile like that is the velocity at the inflection point divided by the velocity gradient at the inflection point, which has the dimensions of a length scale. And the Kelvin-Helmholtz instability, the Rayleigh theory, tells you that the wavelengths of that vorticity wave will be proportional to that length scale, that vorticity thickness. So Mike approximated that by a measure he called LS, which is actually twice the vorticity thickness, and plotted that against all these measurements of large eddies, and got this lovely straight line. And this is one of these eureka moments where you think, we've got it. This is a sort of smoking gun moment. You think, God, you don't get a lot of these in the scientific life, but this was a good one. So that was good. But then the question is, okay, we saw those ramp structures, and we have surface renewal models, which vary on, but what do these eddies actually look like? What are they really like? We know that really lumps of air don't move up and down coherently in turbulent flows. So we set out to deduce the three-dimensional eddy structure. And again, if you're measuring on a single tower, you can use Taylor's hypothesis. As Matthias said, you assume that you've got a snapshot of the turbulent flow, and it's frozen, and it moves along at the mean wind speed. But that's not true either, because the eddies are going backwards at different speeds, and the wind speed actually changes with height. So how are things frozen? It doesn't actually work. It works. It's a good first approximation, but it's not true. So you need to actually measure in 2 points at once, and then you can get a correlation. And when you do that, the first thing you can get is correlation coefficients, where you can measure how the velocity here is correlated with the velocity somewhere else as you move the two sensors farther apart. The equivalent with the Taylor's hypothesis is to measure the velocity here, then wait a bit and measure the velocity again a little bit later, and assume that you're really measuring between these 2 points. And then you can compare with the so-called 2-point correlation with the single-point time-delayed correlation, and lo and behold, they are different. So we know that Taylor's hypothesis works as a first approximation, but when it becomes a vital thing to rely on, you can't rely on it. So we did a set of experiments in a wind tunnel, Roger Shaw and I, and with two sensors, two hot wire anemometers, and we moved one of them around and kept one at a fixed height, and then we moved it to a different height, and built up a 3D map of the 2-point correlations. And by using a technique called empirical orthogonal function analysis, we could then find the 3-dimensional shape of Eddy structure that best fitted the correlation map. And when we did that, we actually came up with an Eddy shape, which was a hairpin vortex with its head down towards the down into the bottom of the canopy, and its legs sort of poking up into the boundary layer above. Now, what we're actually portraying here is a quantity called lambda2. You can try various ways to visualize sort of coherent swirling motions in a turbulent flow. It's difficult to do. An obvious thing to plot is the vorticity, but the vorticity is a local quantity which tells you how much the flow at a point is trying to rotate. It's the curl of the velocity vector. And if you just imagine a boundary layer where wind speed is increasing with height, then taking the vorticity in the y direction, transverse vorticity, it's equal to dw by dx minus du by dz. And of course, that quantity will be maximized where things are changing most rapidly. So the vorticity always sort of ends up as lots and lots of fine filaments, like a rat's nest of hair. Doesn't tell you much about the coherent swirling motions that we think of as vortices. So vorticity and vortices understood more generally are not quite the same thing. So lambda2 is actually a measure constructed from the invariance of the deformation tensor. And it's got some aspects of the vorticity, but also some aspects of the sort of solid body rotation that you get in the kind of vortex that you see when you let water out of the bathtub. So plotting lambda2, and we're going to use that as a general measure, identifies regions where not only is the vorticity high, but there's sort of coherent motion, swirling motion of the fluid. So what we did from our 2-dimensional empirical orthogonal function analysis, we found this eddy here. But the EOF process, and it's bloody hard work, I'll tell you that, it can't tell the difference between vorticity one way and vorticity the other, because it actually finds the eigenmodes that fit the motion in a quadratic norm, and because it's a quadratic norm, really can't tell which way things are rotating. So what we got was an eddy structure which looked like that, but it actually had this one superimposed on it and basically got swallowed up by the second one. And we published this in, I think it's in BLM in 2000. And it's an interesting paper, and it was a lot of work, but it still got things wrong. So this picture here, let's go back to it, comes from the large eddy simulation, where now we have much more information because we have, we can look at the full 3D picture, and we can actually composite many, many snapshots of the flow by focusing on that scalar microfront that we observed all the way back in Camp Borden. At the same time, if you look at the scalar microfront in LES, you realize the scalar microfront, where the ejection hits the sweep, also gives you a pulse of pressure. It's actually, you get more or less the same result whether you use the microfront or the pressure as a trigger. But if you look for places at the top of the canopy where you see high pulses of pressure, meaning an ejection has hit a sweep, and then grab the instantaneous velocity field around that pulse of pressure and do that many, many times and stack them on top of one another, then you get this ensemble average picture, which is now a head down hairpin, sorry, a head up hairpin, which is whose legs are rotating in such a sense that they're pushing her up between them, and the head down, which is pushing her down in the other direction, and together they squash, form a pressure pulse, a microfront. The front one gives you an ejection, the second one gives you a sweep. Now, we took a slice through that. We've taken a slice now through the fat one at the back, where we see the sense of rotation of its legs. They're rotating around in such a sense as to push air towards the ground. And these velocity vectors are, the actual vectors. And the colored area is the lambda 2. So what this tells us is that while lambda 2 identifies the more intense core, the actual structure itself is a bit bigger than that. So we can see the swirl is bigger than the lambda 2, but at least the lambda 2 gets this coherent solid body rotation as well as the vorticity. So what I'm going to do now is take a series of slices in this YZ plane. So like a bacon slicer going through and slice, slice, slice all the way through from the back to the front of this eddy. And let's look at what the velocity vectors look like. So we start at the back, and we're just starting to see the back of the head down hairpin, which is down, seen about 70% of the canopy height. And we start moving forward. We see the rotation now getting more coherent, and the legs are getting farther apart as they go through the top of the canopy, and they're carrying on near the most intense part of the vortex rotation, pushing this very strong sweep towards the surface. Then we carry on, and we start to lose the coherence of the head down vortex at the back, and we now start to pick up the head up hairpin at the front. And now the rotation is in the other direction, and it's pushing the velocity vectors away from the surface. This is the ejection. And then the thing runs away. So looking at the same thing in an XZ slice on the center line, we can see here again the ejection, the region where the ejection hits the sweep, and this sort of funny circulation down between. The 3D picture is augmented now by releasing a scalar from the canopy, and by looking at the region where the scalar, actually what this sheet is a plot of the scalar gradient, and when the scalar gradient is above some threshold, we see the sheet. This is a plot Roger Shaw did, and he also put a boundary around the three-dimensional area occupied by a strong sweep, and it sits between the legs of the head down hairpin, and around here you'll get the thing to rotate. Come on. Okay, I obviously didn't link that one properly. Yeah, it's two views there. In between the legs of the head up hairpin is an ejection. Between the legs of the head down is a sweep, and in between is the scalar microfront. And we do exactly the same thing, but now up in the inertial sublayer, the log layer out of the roughness sublayer, trigger on pressure, and now we no longer get this nice coherent head up, head down. We get a sort of a big blobby head up and pretty much nothing head down. A little bit of a sweep. Buried in there is a very large ejection. Now, Ron Adrian, with a series of collaborators, produced a whole set of papers looking at the flow of smooth wall, mainly smooth wall boundary layers, and showed that in the inertial sublayer, in the log layer, the dominant eddy structure is in fact a head up hairpin. And this is caused because if you have a velocity profile, which increases with height, mean profile, then the mean vortex lines are all transverse lines, Y vorticity, and you give that a little bit of a perturbation, give it a little bit of a kick up into hairpin shape, just by a random turbulent motion. That hairpin will get stretched by the mean strain of the boundary layer profile, and the vorticity gets amplified, and it will then kick off another one, and so on. We're not particularly interested in that for our purposes, but that's what we expect as we move away from the surface, that we won't get vortex pairs, we'll get a dominance of head-up vorticities. But in the canopy, jumping ahead slightly now through a series of deductions, but the canopy instability process, we believe, actually works like this. We start off with the inflection point, which is unstable, and we get a Kelvin-Helmholtz wave in the vorticity. through a nonlinear instability process, those regions of positive and negative vorticity will roll up into transverse vortices called Stewart vortices. Well, those vortices themselves are unstable because each vortex spinning like that is trying to push air in front of it down that way. The vortex behind it spinning that way is trying to push this one up. So every one is actually in balance because you've got one behind it pushing it down, one ahead of it pushing it up. But if you move two of them slightly closer together, then their interaction will start to move them around each other, and there'll be less counter movement from the vortices farther away. So when you have a line of vortices like that, it's unstable, and you let them go, and they'll start to wrap around each other like spaghetti. And once they get strained then by the mean vorticity, mean shear, they'll get stretched and stretched into hairpins, and then self-induction of vorticity, I'm going to go through all the hand-wavy arguments and that, but basically a vortex like that will try to move downwards, and a vortex like that will try to move upwards, and they'll stick together. Now what I'm going to show, this in fact all happens simultaneously, but what I'm going to show you is a series of animations or simulations, DNS simulations, where we start off with an inflective velocity profile with 1% random irrotational fluctuations superimposed upon it. Now, remember Gabby's talk on Wednesday, if you have a small perturbation and the thing is unstable, the perturbation will grow, grabbing energy from its background. So we're going to see whether this actually starts to happen and whether these vortices appear, and then we'll go on from there. So here we have an inflective velocity profile, and what you're seeing here is just a bit of blob of lambda 2 before we start the thing going, and we're trying to choose values of lambda 2 so we can see any emergent structures. And what we see is that this velocity profile is unstable, that coherent vortices will start to emerge from the background, and the spacing is actually linked, is proportional to the vorticity thickness of the original inflective velocity profile. And we can look at that from the top down, and we'll see the appearance of these vortices and where they go. So the initial inflective velocity profile, this is just to show that it really is unstable. And we'll get a whole series, if we imagine now we've got a whole series of these Stewart vortices, they've clumped together to form these vortices. Again, we've got they're sitting in a background velocity profile which has an inflection point, and again we've given a 1% irrotational fluctuation, random fluctuation across the field to see what happens when we let it go. And they, as I said, they start to grab each other because as soon as they move a little bit closer together, they have a greater influence than their neighbors, and they'll wrap around to form these things. If we look at the same thing from the top, what we see now is that there's a selection for a particular lateral scale. Just like the original vortex spacing was related to the vorticity thickness, the spacing both horizontally and laterally of the vortices wrapping around each other is also related one step back to the vorticity thickness. So the overall three-dimensional eddy structure is related all the way back to the scale of that inflection point in the velocity profile. Now, as I said, for convenience, it's nice to present these as a cascade of instabilities. A linear instability, Kelvin-Helmholtz. The clumping into Stewart vortices is a nonlinear instability. The self-interaction of those vortices is a linear instability, and then vortex induction is a nonlinear process. But in fact, in a real canopy, this happens all together. So what we've got from the large Eddy simulation here is we've looked for strong pressure pulses at the canopy top. We've taken the before and after time series from the LES and composited a bunch of these to see what actually emerges when we just let that thing go. And what you'll see is the emergence of a pretty globby, nevertheless clear, head down hairpin at the back, and in front of it, head up hairpin. Now, those nice pictures I showed at the beginning had many, many realizations composited. To get this kind of movie ensemble, there are far fewer realizations which fit the conditions necessary for this, but nevertheless, it's fairly clear that the thing just emerges out of the background as a fully formed head-up, head-down vortex pair. Come on. You can do this all day. License this to some horror movie maker. So individual realizations don't look anything like as clear as that. So that's just a snapshot at one instant of the flow field around the pressure pulse. And what you see is this sort of ragged sort of hairpin here, which has got one leg much stronger than the other. You can identify the pressure pulse. You can identify the sense of the vorticity here, which is the vorticity of a head-down hairpin. So all of those instability mechanisms I described are really come from linear stability theory. Well, the Stewart vortices is nonlinear, but nevertheless, it's sort of mathematics. So we can ask, why does linear instability theory describe this complicated structure in what's a clearly very nonlinear environment, the turbulent flow? And how should we interpret these ensemble average structures? The best way to think of them is kind of as attractors. There's all this stuff in the flow. The flow, if it was an ideal world, would like to arrange itself so as to basically destroy the momentum gradient or the kinetic energy gradient as quickly as possible. This is sometimes called maximum entry production theory. So if you like, the ideal shape is selected by the flow, if we can use this kind of teleological language, to maximize the rate at which we dissipate that gradient. And I've quoted Leo Szilard there, or misquoted, the unreasonable effectiveness of linear theory in predicting large-scale structure in turbulent flows. And in fact, there's a long history of this. There's a field called rapid distortion theory, where in order to predict the structure of the energy-containing eddies in turbulent shear flows or distorted turbulent flows, you pretend that the nonlinearities can be ignored, or at least can be represented by an eddy viscosity of small eddies working on large eddies. A bit like large eddy simulation, but you do it in such a way that you can actually solve the problem analytically. And it works remarkably well, far better than you've any right to expect, given that turbulence is supposed to be a nonlinear phenomenon. And the way I justify this to myself is that the energy-containing eddies are getting their energy from the mean flow, and therefore their structure will reflect the symmetries of that mean flow. The nonlinearities in the turbulent equations really are talking about what happens when those eddies interact with each other and interact and form smaller eddies, which then form smaller eddies, and so on to viscosity, as Richardson said. So surprisingly, linear theory can get you quite a long way in turbulence if what you're interested in is the structural shape of large eddies, which are dominated by by mean flow structures, or mean flow which has clear symmetries. So summarizing all that, the mixing layer hypothesis, observations, as we saw, of canopy roughness sublayer turbulence, distinctly different from what's in the inertial sublayer above, coherent eddies with a single length scale. The turbulent Prandtl number is the ratio of the eddy diffusivities for heat and momentum, or momentum divided by heat. And in the mixing layer, it's observed to be about a half. And rapid distortion theory tells you that the turbulent Prandtl number depends on the history of straining of the eddies. How long have they been subjected to the strain. And rapid distortion theory says that when you have only had a short time straining, like a mixing layer, then the turbulent Prandtl number will be about 1/2. If you carry on straining the eddies, eventually you'll asymptote to a turbulent Prandtl number of around 1, which is what we see in the logarithmic layer. And the intensity of turbulence, the covariance of U and W divided by the variances, the product of the variances, is about 45 or 0.45 rather than about 0.3. So it's more coherent and more good at transport. So as I said, these are characteristics of a mixing layer. There's always an inflection point if you're absorbing momentum over a height. Then we get an instability linked to the vorticity thickness, and then that cascade of instabilities, which really are all happening at the same time, which link the final eddy, which is a head down and a head up, glued together by vortex induction to that initial inflection scale. And we've looked at these things for a wide variety of techniques now, and it's a pretty solid theory. I think it's gone a little bit past the hypothesis. There's one final point, which touches on something that we talked about, a couple of us talked about yesterday, I think. In a linear stability theory like this, the eddy growth rate has got a time scale, and the time scale is proportional to the rate at which things are being strained to give you the instability in the first place. And so this is a shear instability, so the eddy growth rate time scale is 1 on the shear. So what happens is we occasionally get a very large sweep of momentum from the boundary layer high above, and it raises the average velocity near the top of the canopy, lifts it up. And so the shear increases. The growth rate of the eddies then is faster, and so they can emerge out of the background of all this other messy turbulence faster than the messy turbulence can smear them out. So we expect to see these double roller eddies appear in groups linked to a region of the whole canopy being elevated in its velocity and its shear above the background. So when we do measure these things, and we measure the transition velocity, we find that they move downwind faster than the average velocity, because they were actually generated at times when the velocity near the top of the canopy was larger than the average. And that's something we'll pick up if we have 5 minutes intermission. Yeah, let's go to the second half of part 2. So as we looked at on Wednesday, we have a fairly robust theory of canopy roughness sublayer eddy structure, near neutral flow. We've just looked at details of that, links to the inflection point instability. If we use that vorticity thickness as an extra scale, we can modify Monod-Nabokov theory for the extra mixing near the canopy. But this, and there was some evidence from that, I think that's Harman and Finnigan in 2008. And the problem is that this roughness sublayer phi function, this function which corrects for the extra mixing, fails for large negative Z upon L because it's based on the physics of shear-driven eddies, as you've just seen. But when things get very unstable, these shear-driven eddies might not be the dominant thing. It also fails when things get very stable. And if we've got time, we'll just have a quick look at that right at the end. So to try to understand this, for the last few years, we've been working with this very large, detailed, large eddy simulation model that Ned Patton's developed at NCAR with Pete Sullivan and others. So this is a model with 5 kilometer by 5 kilometer horizontal radius size and 2 kilometer deep, with a fully resolved canopy with ball ballooning stomatal conductance model, as we've heard about the last couple of days, 2-stream radiation, and a coupled soil water model. So an active canopy. The simulations have 900 watts per square meter constant incoming solar radiation, and then the canopy energy balance sorts out what goes back out as sensible and latent heat, and energy balance closure is observed. We start with an initial potential temperature profile increasing at 3 K per kilometer. So this is, if you like, before the boundary layer gets going in the morning. And the thing that's varied is the geostrophic wind, varying from 20 meters per second, so strong near neutral conditions all the way through the boundary layer, to 0, so free convection. And looking at 5 things, so neutral, near neutral, moderately unstable, strongly unstable, and free convection. And you've already seen these 2 end members, the near neutral simulation, where you can see clearly the shear in the boundary layer up to 1 kilometer and just a bit above, visualized by looking at temperature fluctuations, and the free convection simulation where there's no mean velocity top of the canopy. So if we look at slices through that last simulation at 6 canopy heights, on the left-hand side, what we're seeing are the rolls that Mateus showed us this morning, which typically form when you have a sheared boundary layer with a little bit of heating. And on the other side, the right-hand side, is the strongly unstable region where we got so-called Rayleigh-Bernard convection cells. I'll tell you a little bit more about Rayleigh-Bernard in a moment. So these things are of order 1 kilometer in size. So the rolls are spaced about 1 kilometer apart. So dark is downward vertical velocity. We're visualizing vertical velocity here, and light is up. So you can see the up and down motions in the rolls. And on the right-hand side, we see the cells with upward movement in the walls, which are somewhat thinner than the cores, which are taking colder, drier air down. So the streamwise vortices that are often observed in the boundary layer. It's a different brown paper, yeah, Andy Brown. And here are some pictures of the fact that when things get more unstable, the rolls, which were originally, in this case, visualized because cloud often forms in the upward regions if the air is moist, those, as the wind gets a bit gentler and the convection is still strong, then the rolls start to break up into cells, these blobs, which are the classic Rayleigh-Bernard cells. So Rayleigh-Bernard convection, keep saying this, is the classic archetypal free convection model that we think about when we think about a boundary layer heated from below without much wind. And so it's a classic experiment where you have a hot plate below and a cold plate above, and you start to fix the temperature of the 2 plates. And as the temperature difference starts to increase, initially the heat flux from the bottom hot to the top cold plate is all by molecular conduction, and there's a steady, a uniform, a linear temperature gradient. And then at a certain Rayleigh number, you remember the Rayleigh number, which is basically the ratio of buoyancy forces to viscous forces and the rate at which conduction smears out the blobs of warm air which would like to become unstable. And the critical value for the Rayleigh number in a situation like that, between a hot and cold plate, is about 650. In the atmosphere, the Rayleigh number is about 10 to the 9. So usually things are well and truly unstable. And what we get then is these boundary layers, these thermal boundary layers on the upper and lower surfaces, and then these small eddies which come from these surfaces grouped together in these coherent plumes which efficiently move heat from the bottom to the top and cold from the top to the bottom. So if we look at the evolution of those atmospheric boundary layer scale instabilities with Zi upon L, which is our stability parameter now for the whole boundary layer, and why those two things are mixed is because L, if you remember, is a stability parameter formed from surface layer values, from U star, Q naught at the surface, Z, what else is in there? G upon T, the expansion coefficient. And from that you can form a length which characterizes the heat flux, or basically the ratio of generation of turbulence by shear and buoyancy down at the surface, whereas Zi is the depth of the whole boundary layer. So by a parameter Zi upon L is telling us something about the way that the heat flux generated at the surface, or turbulence generated at the surface, is eating its way into the stable troposphere above over a depth of boundary layer Zi. So what we see is that as we go from near neutral, at the top left, where we have these clear roll structures, we see the rolls start to become a bit more ragged, and then the rolls starting to break up into cells, and then finally into these clear hexagonal type cells. If you just Google Rayleigh-Benard convection and look at some pictures on the web, often what you see are very clear hexagonal cells like crocodile skin. Just be a bit careful, because these are almost always not really Rayleigh-Benard convection. Those very clear low Reynolds number hexagonal cells are caused by a balance between buoyancy and surface tension, not by buoyancy and inertia as real Rayleigh-Benard. Real Rayleigh-Benard is never quite as clean as that. So as we go through that changing Zi upon L parameter in the boundary layer, there are a series of instabilities which might be responsible for the rolls and then the cells. So when the flow is nearly neutral and you get strong shear, remember I've told you a couple of times now that you don't get turbulence unless there's some viscosity. Well, that's not true. So in fact, you don't get exponentially growing disturbances unless you have viscosity, but you can in fact get disturbances which grow algebraically. And this is called finite amplitude instability theory. So it doesn't depend on infinitesimal disturbances. You've got to have some finite sizes, but they will always then grow into streamwise vortices, but the turbulence, the mean velocity has got to be strongly sheared. These are the bane of wind tunnel modelers' existence, because once you get them in your wind tunnel, you never get rid of the bloody things. They'll persist all the way down the working section. So, you know, they're ubiquitous in strongly sheared flows. So in the atmospheric boundary layer, if it's really neutral, you will get rolls, but it'll be in the lowest 30% of the boundary layer. Won't extend all the way up to the inversion. But as soon as you get some heat, then these rolls, instead of being in the bottom 30%, still pretty big, you know, bigger than the surface layer depth, they'll start to fill the entire boundary layer. And a few instability theories have been investigated to figure out what the origin of these things are. In each of these cases, what you're doing is, as Gabby showed us, we're looking at writing an equation which allows certain interaction mechanisms to occur, putting in a perturbation, seeing if that perturbation will grow. There's a thing called an inflection point instability, which relies on the fact that the velocity, the mean velocity, changes direction from the geostrophic balance above the boundary layer to a balance between pressure gradients and drag at the surface. And Doug Lilly in 1966 produced an analysis that showed that there was an instability that could produce rolls, but in fact, later simulations, which when computers got bigger, showed that that didn't really, it's very hard to observe. It may be there, but no one really knows. There's another instability which relies on vorticity velocity coupling. Don't worry about that, because the real instability which seems to work is the convective instability, and it's primarily this Rayleigh-Benard instability, you know, hot below, cold above, and it generates eddies. Now, there's classic analysis of this instability by Chandrasekhar, done in the 60s, early 60s. And what that tells you, it's one of these classic problems you'll learn as a student if you get into this area. What that tells you is that what the critical Rayleigh number will be. It will tell you the wavelength of the disturbances. What it won't tell you is the actual shape. And it turns out that these hexagonal cells are just one of many possibilities. So if there's any directional information, like a little bit of a wind speed, then the cells will line up instead in rolls. So the rolls are really a Rayleigh-Benard instability mode. So what we find is that as Z upon I gets greater than 5, the Rayleigh-Benard instability growth rate is faster than any of these others, and these rolls will be the initial manifestation of Rayleigh-Benard instability. As you carry on reducing the geostrophic wind, increasing the heating, the rolls will break up and become cells. So that's fine. That's what happens. What happens down at the top of the canopy? So on the left-hand side is canopy top conditions in the weakly unstable case when things are dominated by rolls. We can see the white and the shaded light and dark, meaning up and down motion of the mean wind at 6 canopy heights on the left. And then the blue and red regions denote regions of high shear or high negative Richardson number. The same thing on the right-hand side, but now in the strongly unstable case where we've got cells. So on the left-hand side, what we see is where the rolls are bringing fast momentum down from the boundary layer above, we get strong shear at the top of the canopy, patches of strong shear. And where the rolls are moving up, we get low shear, because the wind's being slowed down by the surface, and it's collected heat. So the Richardson number, remind you what the gradient Richardson number is, it's the ratio of the characteristic timescale of buoyant motions divided by the characteristic timescale of shear eddy growth. Seems to have lost some parallel lines in there, never mind. And they're aligned, these regions of strong shear are aligned with the downdraft regions, the regions of high unstable Richards number aligned with the up regions. On the right-hand side, it's a bit more complicated. So as a cell goes down, if there's any mean wind, when the flow is in the direction of the mean wind, the cell motion adds to the mean wind and you'll get strong shear. But on the other side, the cell motion subtracts from the mean wind and you'll get low shear. So you just get patches of strong shear on the downwind side of cells. Now, if we look in the strong shear regions, below downdrafts if you like, or but in this case, below downdrafts in the strongly unstable case. So in these patches, just on the right-hand side, where the whole boundary layer motion is dominated by strongly unstable motions, but nevertheless at canopy top scale, there are regions of strong shear. We see, doing that compositing stuff we did before, looking for pressure pulses and adding up the velocity fields around the pressure pulses, we see exactly the same ejection, scalar microfront sweep structure of the mixing layer eddies. So in regions of strong shear, even if the whole boundary layer is convective and there's very low mean wind, nevertheless at canopy level, we'll get mixing layer eddies. Let's look at a bit more information. If we look at the momentum flux, U prime, W prime, and we treat the momentum flux itself as a time series, instead of looking at time series of U, time series of W, and correlating them, let's form the time series of UW, which is like a time series of flux, and correlate it with the time series of temperature temperature flux. And for some reason, a theta has become a phi. Never mind that. Should have learned Greek at school. So so basically what we're doing is looking at the correlation between the fluctuating transfer of momentum and the fluctuating transfer of heat divided by the variances. And in this picture, which has become quite well known now by Dan Lee and Elie Bouzid, we see that as instability increases, in this case denoted by surface layer scales, minus z upon L, the correlation between momentum flux and heat flux drops off. It's getting up to about 0.7, 0.6 in neutral conditions, then it gets steadily smaller as things get more unstable. And these averaging operators, the angle brackets at the top, in this case is time averaging. But if we look at our large Eddy simulation results, where we're now doing spatial averaging, we see the same picture. Now we see that in near neutral conditions, we get a correlation between spatial patches of momentum and heat flux. They're well correlated, they occupy the same regions in space when the flow is nearly neutral. But as we go towards free convection, we find complete lack of correlation between transfer of momentum and transfer of heat, suggesting that rather than the picture that's been, I guess, in everyone's minds for many, many years, which is that the same eddies are transferring heat and momentum, but somehow get deformed a bit, or maybe that different parts of the eddy transfer heat to what transfers momentum. This is telling us that momentum gets transferred predominantly in one part of the flow and heat in a different part of the flow. And we can partition then the momentum flux that we measure with heights up to 4 canopy heights by looking at high and low shear regions. So in the near neutral case, what we see is that the momentum flux is higher near the canopy in high shear regions than it is in low shear regions. That crosses over at about 2.5 canopy heights. In the moderately unstable case, similar kind of picture. And of course, there's not really any momentum flux in the free convection case. The heat flux, somewhat different. In the near neutral case, the same eddies would seem to be carrying both heat and momentum. There's not much heat being transferred anyway because it's nearly neutral. But as we get to more unstable conditions, we find that the heat flux is carried preferentially in the high negative Richardson number low shear regions. So what's going on? If we look at the low shear, high negative Richardson number regions, where the large scale motions are coming down to the canopy, or the rolls are coming away from the canopy, and we composite again by looking for regions of high heat flux and looking at the patterns of the flow around them, then we see that below downdrafts, where the air's coming down, we get plumes of warm air moving up from the canopy up into the flow above. If we go below an updraft, remember the air's coming down here, and at some point it's got to meet the air coming up and stop. So we have that contour at 0 velocity. These are velocity vectors. If we look below the updraft, we get the plumes about the same size now, but it now continues up. In the free convection case, remember this is weakly unstable, these are rolls. Free convection case where we have cells, pretty much the same picture, except now the plumes extend for a greater distance up to about 2 canopy heights. So pick your contours to plot. And again, we see downward flow in the cells coming down from the boundary layer above, and it meets the plume coming up from the surface. If we're below an updraft, then of course the plume carries on up. So we have, it seems, when we focus on the low shear unstable regions produced by the large scale motions above, in those regions we don't see mixing layer eddies. What we see are convective plumes. Now, this large eddy simulation doesn't have any spatial structure, any horizontal structure. It doesn't have individual trees. There's nothing to tell the flow how large things should be horizontally. As we saw in the mixing layer eddy case, it was the vertical scale of the inflection point which tells the flow how large these structures, these mixing layer eddies, should be horizontally. So what's telling the flow how large the canopy plumes should be, because there's no canopy structure in the horizontal? It's a picture that Roger produced, and by looking at many of these instantaneous realizations, he pointed out that the size of the instantaneous canopy plumes are always about like the canopy height, of that order. They're not a whole range of sizes. Near the canopy, they're always, in that lower part of the thing, they're like the canopy height. So we thought, well, this is a bit like the Rayleigh-Bernard convection instability problem. But now instead of having a cold plate on top of a hot plate, we've got a hot plate, we've got a canopy, in fact, where we're absorbing radiation, and the radiation will decay exponentially into the canopy, into our canopy simulation. And then we've got an unstable temperature gradient above, which eventually will decay like Z to the -1/3. It's a free convection solution. We won't even worry about that today. So we thought, well, let's see what happens if we simulate this. If we have a model where we have it's the right way around, we have a temperature profile, which is generated by a heat flux profile, which in turn is generated by the absorption of radiation into the canopy. So there's a length scale for this absorption. It's the E-folding distance of radiation absorption, which is set by the canopy density, plus some information about the angle distribution of the leaves, and a bit of other stuff you've got to put in there. But basically, it's a fairly simple calculation to do. So we have a heat flux profile which peaks at the canopy top and decays exponentially with an E-folding distance, which we'll call beta, beta theta, and then no heat source above, and that generates a mean temperature profile, which is increasingly unstable, and at the canopy top, it then is constant. In fact, in the simulations I'll show you, it starts to bend back over and approach the Z to the minus 1/3 free convection large scale limit. So we said, okay, if we do a simulation similar to those I showed you of the mixing layer eddies of this, what happens? And what happens is that the instability starts at the canopy top, where the mean velocity, where the mean temperature profile is most unstable, and the eddies penetrate down into the canopy and grow in horizontal scale, as you see on the left-hand side. There's a preferred scale selection again. So we do see that this situation of absorption of radiation in the canopy, producing a canopy heat source with a certain E-folding distance, translates into a horizontal scale of canopy plumes or Rayleigh-Benard eddies. If I did the larger simulation where the temperature profile stops increasing, then you'd see that these things reach a constant size. So somewhere in neutrally stratified flows, we've got that theory we think it's okay. We use the controlling length scale of the shear instability as an extra parameter. That's good. In unstable conditions, we have the large atmospheric boundary layer scale structures modulating everything. So the mixing layer eddies occur in the high shear regions. In the low shear regions, we get these canopy plumes. And we can explain the nature of those plumes by a modified Rayleigh-Benard instability theory. So let's have a quick look then at the implications for the stuff that we were talking about this morning. And it also links back to the stuff we've talked about plants in the last couple of days. So on the left-hand side, we're looking at the heat source now, simulated by the LES, over a 1 kilometer by 1 kilometer square, 60% of the canopy height. And at the right-hand side, the vertical velocity at half the canopy height. And what we're seeing here, this is the free convection case, is that the large-scale structures in the whole atmospheric boundary layer are being impressed on the canopy. And what we'll see is that the way that that's happening is not directly through the turbulent structure, but through the way that hot and cold air is being brought down in contact with the canopy by those large-scale atmospheric boundary layer motions. So it's interesting, though, in itself that that large-scale structure is still present right down amongst the canopy elements. So if we partition heat flux between updrafts and downdrafts now, we find that up to about 4 times the canopy height, most of the heat's transferred during the downdrafts, which is sort of not what we thought. I mean, we thought that, okay, we've got this large upward movement of heat, these plumes, surely that's where all the heat's being transferred. But at canopy level, it's actually the downdrafts which bring cool air down in contact with the canopy, which maximize the leaf air temperature difference and increase the transfer of heat from the canopy into the air. Now, some of that moves sideways then and goes up into the up walls, but that doesn't actually take over heat transport until you're a few canopy heights above the ground. So we have this sort of almost strange decorrelation between what's happening in the boundary layer above and the mode of heat transfer at the canopy itself. Going back to this picture of the whole canopy in free convection, it's interesting to look. You see here that there are regions where the sideways movement of the cells is given a strong shear, and where mixing layer eddies will be doing the transfer. But then in lots of other places, it's the canopy plumes, which get heat away from the canopy and into the floor, and then the whole thing gets swept into the walls of the ascending cells. So if we look at what are the motions which are doing the transfer, we see that this is the near neutral case, or the least unstable. The heat source, 60% of the canopy height, shows a little bit of structure from the rolls above, bringing hot and cold air down. But the heat flux, the turbulent flux of heat from the canopy doesn't. Basically, what's doing the transfer from the canopy into the air above are all these fine scale things, the mixing layer eddies or the canopy scale plumes. If we go up a bit to 6 canopy heights, now we see that that stuff that came out of the canopy has been swept up and organized into the large scale structures of the whole atmospheric boundary layer. This is clearer, just maybe even clearer, if we look at the free convection case. So the source itself bears the imprint of the large scale structures because it's bringing cold air down, or increasing or decreasing the canopy source. The turbulence doing the transfer, taking that stuff up into the air above, is still this fine scale structure, mixing layers and canopy plumes, until it gets up to about 6 times the canopy height, when it's now got organized into the large scale stuff in the boundary layer above. So putting all that together, I won't repeat all that, you've seen that before. The interesting thing maybe, given the discussion of Matthias's talk and our discussion group, was that, we've got this sort of area or time averaging statistics, which are the outcome of this cross-scale coupling. So basically, we've got 2 different eigenmodes, 2 different instability structures, which can't coexist. If you've got mixing layer eddies and you add some heat, to begin with, the heat will smear out the velocity gradient, which is producing the eddies a bit. But then when it smears it out too much, you won't ever get the eddies emerging from the background, and you'll flip to the canopy plumes. If you've got canopy plumes and you start increasing the wind speed, so initially the plumes will be bent over a bit, won't be as efficient, but when you bend them over too much, you'll flip back to mixing layer eddies. So you have one or the other, with a bit of blurriness around the edges. But that average heat flux and average momentum flux from the surface is what determines what kind of structure you get in the whole boundary layer. But the structure in the whole boundary layer tells you what the pattern of mixing layer eddies or plumes are. So you have this cross-scale coupling, which is an emergent property of the whole boundary layer. And when we look at why we need long averaging times for energy balance and carbon balance closure, the fact is that the eddies doing the transfer, even this simulation, are primarily the small eddies, which we can actually grab quite well by 30 minutes averaging times or the equivalent. But the slow variation in the canopy source sinks is locked into the large scale motions in the whole boundary layer above, which means that the averaging time for convergence doesn't actually solve the bias problem, but it certainly tells you a little bit more about the structure of what's going on. The time needed for convergence is linked to the whole boundary layer timescale, not the near surface timescale. If you give me 5 minutes, I just want to show you one more thing. So we've talked so far about the convective scale. That's what happens during the day. Obviously, energy balance closure is very important during the day. But I also mentioned that things go wrong at the stable side as well. So our shear-driven eddy stuff doesn't seem to work when we go to the stable side. So this was a set of experiments which are linked to this problem of failure to close the carbon balance during the day. So why are we not seeing the carbon that comes out of the soil, primarily out of the soil, but out of respiration during the night? And when this was understood at first, there was a correction proposed by Mike Golden, I think, which said that you can only trust your tower measurements at night if U star is above some threshold. So it's so-called U star correction, so the idea was the turbulence has got to be mixy enough to connect the soil emissions all the way up to your tower. But that seemed to exclude a lot of times when you'd like to still be measuring. And anyway, what was the reason for it all? Well, it turned out, I won't show you all the calculations behind this, that if you, well, let me just go on a bit. We did an experiment where we put our canopy model on the roof of our wind tunnel. This is a heated model. Both the elements and the floor is heated. It's very hard to measure, to model unstable or stable floors in wind tunnels. Because if you remember the Froude, no, we didn't do the Froude number, did we? But the Froude number is the ratio of buoyancy to inertial forces. And the buoyancy forces decrease with wind speed. The inertial forces increase with wind speed. You need to get a high enough Reynolds number in your canopy, in your model canopy, to simulate reality. But then it means that you need a hell of a lot of heat to simulate the right amount of buoyancy. So practically you need your own power station and a lot of fire extinguishers in case things go wrong. But to simulate convective conditions during the day, you've got another problem because the convection starts from the ground. And what stops it going up and up and up is the inversion above. So you've actually got to somehow set up an inversion temperature profile and then heat the ground. But stable conditions are a lot easier because you can just turn the whole thing upside down. So reverse gravity, put the thing on the roof, heat the surface, so now it looks like stable because G is the wrong way around. And that's self-limiting. So stable floors won't keep going. They'll stop when they run out of energy. So we put our canopy on the roof, and we put a hill on it and looked at the generation of gravity currents in the hill. And I'll give you a sort of a lead into this. We already knew from some experiments in a little wind tunnel that when you start to heat the surface, or sort of, if you cool the surface of a canopy, or put it upside down and heat it, then turbulence in the canopy will collapse. It'll carry on being turbulent above, but stably stratified, but within the canopy, the turbulence will disappear. I'll tell you why in a second. And then if there's any hill, the stuff will start to move down the hill and be decoupled from the wind, which is trying to push it over the hill above. And again, some calculations, which I won't show you, tells you that what's important in how strong the gravity current is the length of the hill, not how steep it is. Which means that if you have a flux site with a very, very gentle slope, once the gravity current at night, once the decoupling gets going, then the gravity current will get going and carry soil CO2 sideways, never get to your flux tower. And there are examples of this from many sites, but we've looked at it in the Amazon. So this was from that experiment. And what you see here is the blue curves are the velocity profiles with no heat on. So we had the steady, classic inflection point profile, arrives at the hill, accelerates up to the top of the hill, here we are, and down the other side. When we turn the heat on, we find that instead of going over the hill, within the canopy, that's the dotted line, if you can see it, the flow starts to go down the hill and backwards. So above the canopy, it still goes over the hill. Within the canopy, it goes sideways and down the hill. And if we ran out of heated canopy, this is non-heated canopy, we think if we'd carried on with heated canopy, the gravity current would have pushed even farther upwind. I won't go through this in any detail, except to say that we had this theory for what the exponential profile in the canopy would look like for wind speed. So here it is, and the boundary layer profile above. If we do a similar analysis, it's a little bit more complicated for temperature in the canopy. We still have to have a canopy model, again, for temperature canopy exchange. We get, again, an exponential profile, but now we have the same thing here, but now we have the Stanton number times the turbulent Prandtl number. Turbulent Prandtl number is of order 1, so don't worry too much about that. The Stanton number is about 1.1, and the Stanton number tells us the efficiency of scalar transport compared to momentum transport to the canopy. Now you remember the momentum transport to the canopy is mainly through pressure. There is some viscous drag carried by molecular diffusivity, but for scalars like heat, everything's got to be carried by molecular motion. So there's no equivalent of pressure. So transfer of heat to and from the canopy elements, the leaves, is much less efficient in transfer of momentum. So when we do the calculation for the profile of temperature, it's still exponential, but it decays much more slowly into the canopy than the wind does. So if we now form the Richardson number, remember the Richardson number is the gradient of the buoyancy parameter, the temperature gradient divided by the square of the velocity gradient. The velocity gradient is collapsing very quickly, temperature gradient more slowly. So when we form that sum, the Richardson number as a minimum near the canopy top, where the shear is highest, at the inflection point. But as soon as we get into the canopy, because the velocity gradient shear drops very quickly, the Richardson number goes screaming up to order 10, which kills turbulence completely. And this is measurements in the wind tunnel. That's the actual profile of the kinetic energy production by shear, and then it drops down here. In the wind tunnel, this is what we measured. Richardson numbers of order 0.1 above the canopy, so stable, but not fully turbulent, but within the canopy over 6. So if I can get this thing to run, I'll show you the wind tunnel simulation video. I apologize for the quality of this. This is our wind tunneling camera. This was done a few years ago. So we have a laser sheet illuminating an XZ slice of the canopy on top of the hill. And there's the wind going over the hill. You can see it's fully turbulent above. Within the canopy, it's not completely still, because what we see are the pressure fields of the eddies above the canopy sloshing air backwards and forwards within the canopy. But the canopy air is stably stratified. And if you look closely, you'll see that it's actually moving downhill within the canopy while it goes uphill over the canopy. We'll see this a bit more clearly in a moment. You see the occasional eddy penetrating down there, but the steady downward creep of air within the canopy while it goes over the top. Here we go, a bit more smoke. So this was, remember, this is a very open canopy. The wind has no problem getting in there. It's just that the balance of forces within the canopy is such that there's very poor average coupling between the flow above and the flow within. So the flow within, because it's buoyant, buoyantly unstable, it's sort of heavy and it's trying to go downhill, then that's what it does. So now we're looking down the foot of the hill, and you can see clearly that the air here within the canopy space is moving in the opposite direction to the air above. So this is what happens when you're trying to measure in your flux tower at night. Even if you've got an incredibly gentle slope, the thing which controls the strength of the gravity current is not the slope, but the length of the slope. So I'll just stop that and go back to finish with, yeah, so, and this is the consequences of this. This is at some site, looking at profiles of CO2 through the canopy. This is during the day when things get well mixed. Then the sun goes down and immediately high concentrations of CO2 appear near the ground and continue through the night. And they're just not getting up to where the flux instruments are. So that was a bit of an epilogue. So this profound change in turbulent and flow structure when you're stable, again, this is a whole of canopy emergent property. It's actually produced by this leaf level process, the Stanton number, the ratio of efficiencies of momentum and heat transport at the leaf level. And if you like, you can think of this switch in flow structure to fully coupled to decoupled as a movement to a sort of a stable attractor for the canopy system and away from the neutral convective attractor. And that happens very fast at sundown, and it gets broken down very quickly in the morning. So I think that is indeed the final comment. Thanks.